Hello everyone, welcome to the webinar. Before we start, I just wanted to start with this slide. Just think of how if Amazon starts shipping items towards your home even before you place an order. Yeah, even before you place an order. So it looks crazy. Interestingly, it is true. And thanks to AI, Amazon is sort of using some of the AI techniques to analyze the historical buying patterns and the browsing habits, the wish list, and demographic data, and so on, to really predict what you're going to buy next. So effectively, Amazon knows you better than you know yourself. So if you see the business value here is they can ship the items in advance to cut down the delivery time. If you really fast forward, the future scenario will be something like you go to Amazon website, you select items, and you click on order button. You'll see a doorbell ringing with the Amazon delivery boy, with your items, whatever you order just now. So that is the kind of the power of AI you see. So if you really see back, the progress on AI has been phenomenal over the last few years, impacting many fields. So in today's webinar, you will learn some of the basic introduction on the AI, the artificial intelligence, and some of the technology landscapes in terms of the technique used in AI, and few sample industrial applications. Then the software engineering, how the software engineering is sort of evolving, what is the complexity involved there. Then it's more of the cross pollination of how some of these artificial intelligence techniques can help in resolving some of the software engineering, the problem statement or the challenges that we see day to day. So as part of that, probably we'll cover some of the use cases in software engineering, like in the requirement engineering. What is the kind of challenges we see in the modern software, and similarly in the continuous development and the continuation integrations. So that is what we're going to learn in the next 60 minutes. So a quick brief intro about me, myself, Yogesh, a staff engineer, a senior technical member in Honeywell Aerospace, a part of technology and strategy team, trying to bring, explore or develop new technologies that could help in the way we do software engineering much more efficiently and effectively. So I have 2 decades of experience in the software development, the verification and certification of Avionics safety critical systems. And I'm fortunate to work on some of the state-of-the-art products that keeps the passengers and the plane safe when you're really flying, like the cabin pressure control, the flight management, most different subsystems in an aircraft. And my education, I'm basically in engineering and computer science and a master in software systems. I hold several patents and trade credits in some of the avionics systems, like prognostic maintenance, navigational radio, and software reliability. So I worked on most of the aircraft that we see in in the current and last generations. So coming back to the topic, the first one is this is a webinar where we're trying to see the convergence of two different streams. One is artificial intelligence and the other is on the software engineering. So to start with the basic intro of what artificial intelligence, what I pursue as artificial intelligence is, it's basically it's an ability of machine to emulate the human behavior or the human intelligence to solve some of the complex knowledge-based problem statements. When I say human intelligence or human behavior, basically I meant to say the way a human reads, a see things or a pursues, and a speak or a learn, sort of makes its decision making. So that's what the behavior. So basically, and when you say intelligence, the ability to really retrieve the data, correlate this data, and identify some pattern to make some decisions, which is more efficient and effective. So that's what the artificial intelligence. I think you may see several definition of this. This is something that I feel it's close to what I understand. Again, the good thing about the AI, the great thing about AI is that it's constantly evolving. Went through several waves of technology developments in terms of techniques, the algorithms, or the tools that you see. So if you see as on they probably the broad, the technology which are more matured and being used in several industries or domains, if you really classify, probably it will fall into this category. The machine learning, which is more of a predictive analytics and deep learning. You'll see, I'll talk about some of the examples of each of these techniques in the subsequent slide. The other one is speech. You see wide varieties of applications, both text to speech or speech to text. Again, the vision, it's more of a computer visions, the image recognition, and the processing. Then on the natural language processing, in terms of classifications or the translations or the data extractions, deriving some meaningful insight out of the data. Similarly, the expert systems or the robotics. So these are probably, there could be a few others, but I would say some of the matured the techniques being used in several industry at this point of time. So, just to quote some of the industry applications now of where AI is being used currently. Some of them, I'm sure you may be already read about it and aware of it. Just to talk, right? Automotive industry. You've seen a lot of advancement in terms of the autopilot features, driverless cars. Again, it uses the AI techniques, basically the powerful combination of the computer vision and deep learning. The computer visions to really recognize the objects and classifying those categorized objects into different type, be it a signboard or a traffic light or maybe moving objects. Again, if you say moving objects, it could be several behavioral patterns you could see in the moving objects, like a pedestrian or a cycle, or maybe a car. The rate at which they move, the characteristics of how they are going to behave is slightly, varies, right? So that is more of object recognitions. Then the deep learning, basically making the right decisions based on the real time the data that it sends in terms of the objects, because what could be the next move by a pedestrian compared to a car may be totally different. So this deep learning has to really make the decision of what should be his next move based on the real time data more efficiently. So there you see a lot of applications of these AI techniques in the autopilot. Similarly, you'd see in the service industry where we see a lot of chatbots or a voice virtual assistants, we call it a smart assistants, which again makes use of the AI techniques, specifically the speech, the natural language processing. You've seen some of the smart assistants which can understand the context, and converse so naturally. It's like any human being, to book some of the appointments or the reservations for you. Basically, it relies on the machine learning model drawn from the real world data, and also it combines the speech recognition and the text-to-speech synthesis with wide range of contextual details. So again, this is one good use cases are the applications of the AI we see here. Similarly, in the planning and optimizations, I think predicting what should be, because if you take some of these sales industries, retail industries, maintaining the most optimal inventory is a key thing, right? So if you have some, many times you've seen that probably you'll hold stocks more than what is really required, and sometimes you run out of the stocks which is really on demand. So AI can play a big role there to really predict based on some of the historical pattern, the buying patterns, overlap with the timing to really predict how much sales is required, so that the retail industry can really go with the right optimal inventory. Again, other industry, if you see, probably healthcare is one of the most important field that AI is transforming. Especially, it's assisting the doctors in analyzing thousands of medical parameters and the medical images to really predict the medical events in advance. Because in the medical, even if you could predict something, a medical event, say a risk of cardiovascular, a cardiac arrest, or maybe an heart attack or a diabetic, in advance, if you could treat the treatments little early, it should be much more effective. So that it plays. Humanly, it's impossible given the volume of the medical images or the data that you see to really correlate the data and come up with these decisions. So these are some of the applications of AI we see in the industry. Then coming back on the other track, on the other side, the software engineering. To simply put in, when you say software engineering, it is more of engineering approach to develop or operationalize or the maintain the software, right? And if you really go back and try to characterize the complexity of the software, right? Some of the data points could be the complexity of the underlying problem that we are trying to solve with the software itself is one of the you know the key contributor in terms of the complexity. Because earlier traditionals, some basic algorithm too, we are talking about some of the autonomous vehicles are most complex applications. So then other factors could be the number of hardware components the software is trying to control and monitor, right? Or if you characterize based on the number of modules, the software, the lines of code that you try to have it in a software, you see that there is a in all these aspect, either you take it in terms of the data and control couple you see between modules, or the source of lines of code, or the decisions or the conditions points in the the software, it is exponentially growing, right? It's exponentially growing. Anyway, if you see some of the maybe the previous generation of the aircraft, since I'm from the avionics background, if I really take that example, we used to see anywhere between some 2 millions of line of code. But the latest generations of the aircrafts, you see close to around 20 millions of lines of code. So that is the complexity that we are talking about. Again, if you talk about Microsoft OS, it has anywhere between 50 million, millions of lines of code. So the software is also growing. The complexity of the software is also growing exponentially. And there's a lot of evaluations now. I mean, in terms of the technical developments happening, we see, be it in terms of programming language. If we take, traditionally used to have more of assembly programming, where which is more closer to your the hardware or the processor, with no almost no abstraction from the hardware. You need to know some this the machine instruction and the assembly code to really write any programs. But that is gradually sort of evolved to reach a state where it is almost completely abstract from underlying hardware that you're using it. Or in terms of methodology, if you see, it is to be structured programming. Then you see next generations where people move more towards object oriented, the model based engineering. So there also you see there is a lot of technology developments happening. And in terms of the the methodology, there is a lot of innovations in terms of traditionally it used to be a waterfall model where you have a sequence of activities. Yeah, that may fit for some of the simple product, but when it comes to the current situations where the time to market is very critical for any product, probably that may not really suit. You need to bring the product to the customer quick, early, get his feedback. That's where you see there is a migration to a different methodologies like DevOps or an Agile. So here also you see, if you really summarize, there is a lot of development happening even in the software engineering side, and also the complexity of the software is also gradually, I would say exponentially, it's growing in terms of the challenges that we face it. So we see two independent now. That's where we need to really see that okay, there is a lot of developments happening in the AI. How we can leverage some of the AI techniques to solve some of the problems we face in the software engineering industry. So we'll talk about some use cases. Again, this is not the only list. There could be n number of applications. I would say it's maybe just a drop of water in the oceans. You may have lot more to do behind these ones. So we'll talk about the use cases, not too much emphasis on the underlying algorithms, because the technology, the techniques, or the algorithms you could use, you get wide varieties of algorithms available with some strengths and limitations, but we'll touch upon one or two what we sort of trying to explore, in Honeywell or what we've seen in outside as well. So the first one is on the requirement engineering. So I just want to now before we get into the what problem we're trying to solve, I just want to give some data points in terms of why requirements, writing a good requirement is so critical in the modern software that we see. One is, again, this is from for the last 3-4 years data from the actual program that were executed, is close to 80% of a rework in any a big software project is mainly traced due to the requirement errors, the poor requirements. So that's a big number. 80% of the program rework is from the requirement errors. The other data point is the cost of fixing your software. If you detect an issue after the product is released or launched to the customer, compared to if you detect, okay, as and when I see a review requirement or the requirement phase itself, it's 200x. This is the, again, the industrial data, 200x. That means you could have prevented the 200x cost if you could have identified the problem early in the program. So that is the kind of impact now it has on the requirement. The good requirement has an impact on the overall on the program. And another data point which is really good, especially in this where time to market is very critical. The 47% of the programs missed their milestones or the goals in terms of cost and schedule, purely because of the requirement issues. So if we really correlate all these data points, requirements is a foundation for a software engineering, and it's very critical. So that's the the big picture. When it comes to the actual or the problem that we face in the ground level is why this kind of requirement issues. If we really trace back, there could be many reasons, but if you really pick the top reasons for issues in the requirement, we find is mainly because we write requirements in more of unstructured natural language, right? It's a free flow English statement. Everybody going to around write the requirements in their own style, yeah, right? So the moment you use a natural language, free flow natural language, it is bound to create, bring in the ambiguity, the vagueness, or the subjectivity in the requirements, or and conflicting requirements. If you talk about some of the complex requirement, I mean products or systems where you have say several thousands of requirements, it's really difficult to manually go and really check all the requirements for a consistent check. What I write in one requirement probably may conflict with other requirement which is there maybe 100 pages down the document, or maybe totally handled by someone else. And other, one of the problem we see is non-testable requirements, right? You write a requirement, but at the end of the day, especially the avionics products where which is completely regulated, the certification is regulated by the Federal Aviation Authority. You need to have a thorough testing is done, and many of the cost is because the requirements are non-testable. You end up rewriting the whole thing at the end. And many times the missing triggers we find, it is an incomplete requirements where it talks about something but it is not clear when that event happens in the system. So these are some of the the issues we typically find in the complex software when the requirements are written more of an unstructured natural language. Example, just to quote an example, I'll try to give from the aerospace domain, but you may have similar thing in other. If you say a requirement which says a software shall set a flight phase to take off when the altitude is between say 50 feet and 2000 feet. Okay, there is another requirements maybe somewhere down the line which talks about set the flight phase to climb when the altitude is between say 1500 to 25,000. So if you see these requirements, they are mutually conflicting because what is the state of the flight phase when the altitude is between 1500 to 2000, because that is a overlapping thing. So there could be several critical action system action that may take based on the altitude level. Maybe it will try to the systems may set the cabin pressure based on the altitude, but if you have these requirements, you may end up developing a wrong software which can be catastrophic. But can we really find some means? Can AI help? Because we've seen a lot of application of AI in the other industry. Can AI help in requirement engineering? Okay, so that's where now we try to explore. Now we see some good results. I believe others in other domains must also be trying. That's where we see a lot of techniques and tool suits here. So the AI technique that can help in engineering, requirement engineering, is natural language process. The foundation for this, I would say, it's more of a domain. I mean, the ontology, the domain specific ontology definitions. The first step in this NLP. When I say domain specific ontology, basically you're modeling the domain knowledge. It's sort of having a common vocabulary of how to represent your domain in terms of identify the system objects, the events, the conditions, or the response, the states. Example, now for you to understand, suppose if we talk about a Avionics software, where the requirement is something like it's basically say take a case of the communication system with an ATC. The flight takes off from departure and arrives at a destination if that is a requirement. When I say ontology, if for this set of systems, basically you're identifying what are the object subjects, what are the predicate, what are the objects. In this case, subject could be aircraft, a predicate could be flies, which is an activity. It could be takeoff or a landing. The object could be an airport, which is departure and dimension destinations. So basically, now you're representing your domain in terms of these subjects, predicates, and objects, which can be correlated with your system's inputs, outputs, and the system's responses. And there are a lot of again, you have an attribute for each of these objects in terms of right, the examples of say airport is an object. The attribute could be more for departure or destinations. So there are a lot of the cards and open source tools available to define the ontology for a domain, like DARPA, and each have their own strengths and limitations. Probably a systems which is more of a logical based systems, the kind of tool you may be totally different. But if it is more of a banking software which is more of a database intensive, the kind of the tool that you may have to use it may be totally different. So here another example I quoted for the banking software ontology. Just to summarize, you're sort of representing, modeling the whole domain. So having a common vocabulary of representing your your system, so that you have a common understanding between the users things. So that is the first step in this case NLP. The second step is basically you subject your the requirements which is written in the natural language unstructured requirements, where typically you will have the textual analytics of your requirements will have lexical analysis and syntactic and the semantics, where basically you parse those requirements, tag them with a part of speech, then group them, then at the end basically you have the list of lexicons now which are aligned with your domain terminology. In this case, it could be in terms of the inputs, the outputs, what are the relations between those inputs, outputs, everything. So once you have this, the past requirements, there are a lot of open source tools that are, or maybe the cards tools that are available, which can convert this data to more of a formal or a semi-formal specifications. It could be a linear temporal logic or a Z notations, where now once you have translate these unstructured requirements to more of a formal spec, then you can run a lot of formal analysis tools which can really check for this the consistency between the requirements, the correctness, the completeness of the requirements. Example, you see that one sample notations that I showed here, where the past requirements can be represented in the notations, where your analysis tools can go and run on those formal spec to really find out if there is any the incompleteness or whatever the issue that we saw in the previous slide in terms of ambiguity, the incompleteness, those things can be clearly brought out from these things. It is like you could correlate to the way we run a static analysis tool on the source code, where you can define n number of rules to really check whether the code compliance against those rules, right? Similarly, you can write such rules on the requirements, which the analysis tool can really go and do it. And we found that now this seems to be very useful. When we tried, we are able to really sort of identify a lot of requirements which we typically find it, especially the inconsistencies between the requirements and the incompleteness. In terms of algorithms, as I said, for the NLP, there are a lot of algorithms. It had be a hidden Markov model. And from the programming perspective, you have R or a Python NLTK with a lot of built-in library, which you can really make use of to do this. Okay, that is the first one. So if you move on to the second phase, right, it's more of a continuous development. Again, to before we talk on some of the areas, where AI can be used, I just want to give some data point in terms of uh, what is the cost of a coding error could be. Okay, coding error, or how critical it is to really ensure that the coding defects are sort of addressed early. This one, I'm sure you must have heard about this another mission, which is the France. Somewhere in 1996, they developed an unmanned Ariane 5 rocket. So decades of development and hard work went into this. In May, developing this rocket and this payload, and the rocket was launched on 4th June 1996. So that was the thing. But what really happened after the launch, this was a little surprising. Actually, the rocket exploded just after 40 seconds after it leads to liftoff. Okay, and they did a lot of, basically it sort of deviated from the desired path and blasted off. So a lot of investigations went in, to really understand the root cause for this, and they came up with the summary report. Okay, summary report, probably it's a quite big one. If I want to really crisply summarize what was the outcome, that is the cause of failure is much more surprising. The cause of failure is one line of source code error in the navigation system. Basically, it's inertial reference system there, where there was a line in the code which was trying to assign a 16-bit value to a 16-bit integer. Basically, the 16-bit variable was holding your rocket horizontal velocity, what should be the next speed or the directions. In the computation in the code, it was assigned to a 16-bit variable. What happens when the value is sort of exceeds more than 32,767, basically, which can be represented, that is the max value that you can represent in 16-bit, right, 2 power 16. So when the value exceeds that one, it took some junk value. It's unknown. And guided the whole directions and the speed based on that on the value. So the reason I sort of quoted this example, and this incident is, even one line of code error can be a catastrophic. If you really see what what they really went back and did, they just corrected one line. They washed out the whole 20 years of hard work they did it. So that is the kind of the complexities that we see in some of these avionic systems. Now, coming to what are the problems now we are trying to solve in the continuous development is one is like we saw in the earlier case, right? Amazon is able to predict what you're going to buy next, even you place an order, right? Even before buy it. If you're putting the same analogy in this case, can you predict the coding mistakes even before the developer make them and prevent them, right? Logically, if you can do that, we can do it here as well. So that is one of the problem statement. The second one is typically, when you write some of these, our avionic, I believe it's the same with other domain as well. It will go through several revisions. You deliver a product to your customers, they come back with additional features. You go back and implement, right? You add a new features, you make one more release. But given the complexity of the software in terms of the lines of code, you have millions of data decision points and so much of tight data coupling between coupling between the software modules. Every possibility is that when you introduce a new feature, it may affect some of the features and some of the software models in the other area. It may go on and fix some of the other areas, right? And because of all this interdependency we see. But can we, okay, when I had a new feature, can I go and run all the tests to confirm that none of the other software, other part of the software is affected? Practically, it is impossible. If you take even some, a simple avionics system, you may have thousands of lakhs of tests, okay, for a given aircraft. So can I go and run it? Probably you need a few months to rerun all the tests to confirm that the other part is not affected. Then how do you do it? So can AI help in proactively identifying what are the most likely impacted components? Okay, when I make some changes to my software, what are the other components, other software modules which are most likely to get affected or impacted? Then identify the test around those functionality alone and run instead of rerunning everything. So you're really cutting down the regression. We call it as regression, cutting down the regression and make it more optimal and efficient. Okay, so that's where this can really play a big role. This is something that we sort of explored and have seen a lot of companies as well done this one, where we are using the machine learning and the predictive analytics to solve these problems. Basically, how it works. The step one basically is the number one is you feed in the historical defect data, right? Which is you have now over several years of and the program's data, the historical defect data in terms of the coding errors, or it could be the requirement design, all the the data that you have, and the resolutions. What are the kind of defects you found? What kind of resolutions you took? Then also, what are the kind of issues that were reported by the field during the integration testing? Basically from all levels of tests, you have the data. Then, for every release, what are the kind of updates it went in? Example, for release one, hey, what is the kind of requirements I really updated? What modules got updated? Then post that one, what are the kind of defects I saw? What kind of the other software models that gone through changes in the subsequent releases? Now, is there any correlation between what model change? What is the next set of models that are getting modified in the next release? So that is the data is the first steps where you feed into this model. So now you train your model, you train your prediction models with all this data, where it can really go back and identify the different inputs which is really contributing, how each of this now is sort of contributing to your the defect that you see, and what is the relation that exists between each of these input variables that we see, and now you come up with some sort of a probability distribution for each of these inputs in terms of how it contributes to the final defects. And also once you sort of analyze these the huge set of data, find the patterns in terms of, hey, what when I modify model one, what are the other models that are impacted, which got modified in the next release. So you build a pattern, come out with those insights and the patterns and build the prediction models. So we have seen that that the more the data you have, the longer your prediction model could be more accurate. To really pinpoint and identify in advance, most likely these are the areas where you're going to have an issue in the next time. I mean, just to quote some of the real-time data from this model example, we have seen that most of the defects data, you see that whenever there is a interprocessor communications, or when you're trying to process some of the data from the other external systems, they are more prone to the defects. That is one of the insights now from your prediction model. So like that, you may have several now the insights you may get. So when you pick up a new functionality, probably a example, I'm just giving a flight management functionality. It can tell you that a flight management, typically these are the kind of the requirement issues we had in the past. This is the kind of defects we found during the design, probably at the test. These are the kind of the field issues found, which can, and also this is the kind of resolutions we took for this defect. So upfront it can tell you even before you really develop, most likely based on my historical data and these predictions, these are the kind of defects you're likely to make, and now and helps the developer to really act upon that. This is just some sample data where you have different parameters will indicate how each parameter is sort of influencing your target variable. In this case, when I say target variable is a defect, how each of these parameters is contributing. When I say parameter, it could be the programming language that you probably the author, the functionality that you're working on, or the system that you're working on. It could be n number of the more the parameters you have, the more data, the predictions could be much more accurate. Okay, again, this is another outcome from this the regressions, the predictive analytics in terms of when you feed in all this the last 10 years of maybe several years of historical data. Some data are direct, some data, okay, when I touch this, the how to interpret this data is basically when I touch a parent function 1, hey, these are the a list of impacted functions, say function 1 and function 2. I have seen that every time you touch these parent functions, you end up in modifying these 3 5 functions. Okay, so now you don't have to really go back and rerun all the test suite that you have. You run this prediction model, okay, then get what is the kind of the function, the impact it's going to, what kind of functions are the software model is going to get impacted from this one. Then you can narrow down your regression only to those tests related to those modules. So this is very very useful. We felt probably that's something that is can be used across them. I believe you have a similar problem statement across different domains. Okay, coming to the probably the last ones before we get into any questions is the continuation integrations. Continuation integrations, typically when it comes to the verification, the testing, two problems we have seen, commonly seen is typically the test development effort takes a lot of effort, right? That is, if you really see within the testing or the integration life cycle, probably that is one activity which takes more time, because the tester has to really look into the requirements, understand what the intent of the requirement, come up with some strategy, test strategy to really how to test it, then develop the test, then you go and execute, right? So definitely that is I would say core engineering within the testing life cycles. And considering that we have seen that the complexity of the software is sort of growing exponentially, right? You have requirements which are so complex. You may have some more than 20 conditions or inputs for any in the requirements. Trying to test manually come up with all combinations, say 2 power 15 combinations of test cases to verify, not to test this requirement is really tedious task, right? So and it's bound to mistakes even the number of that requirement get complex, and the number of tests you have to write is quite huge. It is quite possible that you may miss out some of the critical ones. But as you already seen, one critical code error can be catastrophic. So we cannot really take on that chance. That is one problem statement. Second problem statement, I'm sure there are a lot of GUI intensive products, right? If you talk about the avionics, we have a cockpit displays. Similarly, if you go to railways or automotive, you have a lot of the displays units, the cabin displays for a driver or the or even in the medical industries, there is a lot of GUI based intensive products where the graphics, the graphics, how the data should be displayed on those display screens itself is a requirement for me, graphics requirement, right? So typically my understanding is that these requirements, those GUI requirements are verified through visual inspection, right? Manually, somebody has to really sit through in front of those components and test it. So given these problems, trying to see, hey, is there any AI technique which could really help us is what we're trying to explore here. So the uh, the results are encouraging. I think there is a lot can be done in this area as well. If you talk about the test design automations, okay, instead of tester really go through the requirement, can we have some AI which can analyze the requirements and come up with test on its own instead of with a manual intervention? Probably the manual intervention could be in terms of the defining the test, but the rest of the day thing, can AI do it? Yeah, we find there is a let's say encouraging answer in terms of NLP. We saw that in the previous slide, right? Requirement engineering, NLP can be a big enabler to really do the textual analytics of your unstructured requirements and trying to bring out the meaning in that requirement from the domain knowledge perspective. That means based on the domain ontology, it can really identify for a given requirement what is the object, what are the subject. So if you try to relate with the domain, what are the inputs, what are the outputs for that requirements, what are the triggers, the conditions, and system response. Okay, so that is the the output, I would say, from the NLP, the first stage of the analytics of the requirement, textual requirements. Once I have the data, basically I can write, I can feed it to create a true table, right? Once I know, okay, this is the requirements. I'm just giving an example here. If A and B and C, so I have done this NLP. Now I try to pass this requirement and identify what is my inputs, outputs here. What is the conditions? What is the relation between those objects? In this case, and or are the inputs are A and B, C, and output is if you're setting something in the statement one, say D is equal to some value, so D becomes some output. So you're identifying, extracting those information. This one, then you can create a true table in terms of what should be the values for each of these inputs, and you know the relations between those inputs. You can also automatically find out what will be the expected value for those each of those outputs. So this NLP can really build that logic of creating a true table from these requirements, the parsed data, and build a set of two test vectors, or the test set that you can go on, that is required for a given requirement. Example, you just imagine if you have a requirement with say 2 power, n inputs, it's a 15 inputs. It can hold 2 power n combinations of inputs, right? Just now think of a testers really going and writing all those 2 power n combinations and really picking what is required to meet some of the certification guidelines, in our case D178. It's quite tedious things. That's where AI can really help in building the true tables in terms of what should be the values for this all these inputs, what should be the number of test sets and the input and output. Once you have like some operational data, operational range for each of these input outputs with a combination, you can really go and feed in the actual values based on the true table. which can become for you a test vectors or the test procedure itself, which you can go and execute. So if you really stitch all these things where you have an NLP, now which can go and really parse the requirements and build the truth, the semantics, the objects, then you have a two table generator which can go and generate the different test set that is required to run, then the final test. So you have the automated solutions. The last piece, as I said, right, it's for some of this GOE intensive product like the medical instruments or the um, cockpit display or the car, the this one cabin. There is a lot of the UI intensive products which you have to test. Typically, we do it's more of visual inspections. So can AI help in automating some of these visual inspections which are done manually now? So if you really go through, yeah, answer is good, encouraging. There is a lot of techniques you could find in the AI, like TensorFlow as a rich library of for image recognitions or image similarity detections, where if you feed in what is the expected image and what is the actual image, okay, if there is some means to grab that and really feed it to this, it can come up with, say, what is the similarity, right, whether the same or not. You don't have to really sit in front of the desk. There is the convolution neural network, a technique which can also be used. Or there are several techniques like pixel by pixel comparisons, or your OCR techniques, which can be brought into your software engineering to automate some of the graphical the verification that we typically do it. Okay, so if I sort of go back and summarize it, we saw that AI is parallelly sort of evolving. We see a lot of technology developments in terms of there are several techniques in terms of machine learning, predictive analysis, speech vision, everything, and we see there is a industry applications of that. The other side, we saw an examples of how software a sort of software engineering sort of evolving, the kind of complexity that we see in those software engineering. Then we're trying to see how some of this the AI techniques like the NLP, the predictive analytics, the computer visions can be used to solve some of the day-to-day some of the challenges that we see in the software engineering. Okay, so again, it's a lot of credit to the sources where we sort of refer during our internal development, or just as a reference to understand now what's happening in this area, what kind of strengths and weakness. This really helped. So I'll come back. This is what I had now planned for these sessions. So I'll open up for any questions that you have. I think we have close to around 5 minutes. Yeah, 10 minutes we have. So you can post your questions in your chat window. Okay, let me read out. It's very difficult to read. No, okay, couple of questions I would say. How NLP to meet certifications? Do you see issues using? Okay, the question is, do you see any issues on using NLP to meet the certifications aspects? I probably I'll talk with respect to the Avionics standard. I'm not really sure about the other automotive or the other industries, but in the avionics industries, at least the way I see is example, we saw a use case of where NLP can be used for say automating the test development. Okay, so you have a certifications, the guidelines and the objective which says that the test that you are generated are correct, right? So as long as you review the generated test against the requirement manually, uh, there's absolutely no issues in certifying such products. In this case, you can use this NLP, generate all the tests. Basically, you are avoiding the effort that you are supposed required, which you would have done manually for writing those things, but it is auto generated. But when it comes to the review of the output, in this case the test generated, has to be manually reviewed, so that certifications as no issue. But in case if you say that I want to avoid the review of the output generated by this NLP, yes, we need to go back and sort of qualify this the whole NLP algorithms. I think considering if you really go based on the cost, the ROI part in qualifying that, and the effort you would have spent in reviewing the generated artifacts, probably I choose the second, the later one, where it's worth maybe it's better to go and review the generated one than go and qualifying it. Hope it answers your questions. Okay. Second, how accurate are the prediction algorithms to predict the defects? Yeah. Probably I would say my answer is, see, when you say predict, if you really go back to that prediction, the defect predictions, the input is the data, right? The historical data that you're really feeding in to build that prediction model. Now, so the prediction model, the accuracy of prediction model is as good as the correctness of the data. So if you put uh, uh, incorrect data, more of an incomplete things, the accuracy you get maybe again may not be so worth. But if the data is accurate, now we see probably, at least from the defect prediction context, I would say anywhere around getting 70-80% of the accuracy is something easily achievable. That means probably you can predict 7 out of 10 defects upfront if you have a proper well-trained prediction model with a lot of data things. That would be my answer. Okay. So there are a lot of questions. Probably I'll have to pick some of them. It's not fully showing. Okay, that's not trust. Domain or okay. One is the regression predictions. The question is, why can't we use the traceability data for regressions? What is that additional things? My answer to this is right. Definitely, requirements traceability could be one of the data which is used for regressions. That is more of a direct, I would say, direct impacted things you can get from the traceability. Okay, what are the models that are directly impacted by the requirement? You can pull in the data. But if you really look at the complexity of the software we are talking about, the systems, the modern software we are talking about, which runs to millions of code, and you have the millions of decisions points, and so much of coupling between software modules. It is very difficult. It's I would say impossible to really predict just purely based on the traceability data. You may not have really established the traceability to all those modules, but it'll get sort of an impacted. So yes, requirement traceability, we can use it, but that will not help you to really identify all the possible infected tests. I've seen many cases where you go purely by the requirement based traceability, you test it and release it, you find some other model got broken in the process, and you get back there's an issue from the customers where you have to go back it. So I would say it should be a combination of this traceability data plus some of these the predictions that we are talking about here, which is purely more of a the coding, the considering the complexity of the code, that data is very much required for this analysis. Okay. Okay. other question is the tooling for AI is matured for the application of the same in software engineering domain? What are your comments on that? Can you, okay, yeah. So the question is, now, the tools and the techniques and the tools that we are matured enough to really go on the, sort of use it in the software engineering. I said my input for this probably is, now, we saw some of the, the challenges that we see, on a regular basis in the software engineering. So these techniques will definitely help you to, uh, resolve or find a solution to those problems. Be it a requirement, say in this case of requirement engineering, we talked about formal specifications. Similarly for the code defects, predictive analytics, those tools. I would say the maturity of this tool is sort of varies. There are some tools, like if you talk about formal spec and the analysis, there are cases where there are, some programs which were developed using these ones and even certified, which are flying now. And in the meantime, there are cases where it's still in more of an exploratory and more of an experimental basis. It may not be 100% accurate, but there is a lot that we can really use it in the software engineering context. These tools. So it is more of, it's a continuous. See, the AI was there for the last several years, right? So it's sort of continuously evolving it. But there are pieces which can be really used in the, the matured enough to go and use it in the actual product, even for a certification credit. But others more are, can be used to solve some of the problems that we see it. Okay. Any other questions? How much time we have? One. Okay. Let me see one more. So just similar question. Yeah. So, okay, another question. Is there any tool available currently to identify the predictive testing while we made changes? In the code. Okay. Yes. As I was telling you, right? There are a lot of, I would say, the way you see these say technologies in terms of predictive analytics is, one is the algorithms, the kind of algorithms that it uses. Like you have several algorithms like a regressions, regression based or a random forest. So that varies based on the kind of applications that we are trying to target. Example, now if the output, the target is more of a continuous, which is there is no linear relations, probably you might have to go with random forest. But if there is a linear relations between the input variables to the target variables, then probably you have to go with the regression based things. So that is, again, if you want to really improve the accuracy of your predictions, probably you may have to go with a combination of several such techniques. So that is on the one layer. It's more of the method, the algorithm. In terms of programming, I think commonly used programming, at least I have seen, is R and the Python. And the Python has the rich library of from this for the prediction models, which where for all these regression models or the random forest we talked about, it has the built-in library which we can define and train the models and test it. So in terms of there may not be a separate tool, ready-made cost tool, which will do the prediction. At least I'm not aware, but definitely you can build your own tool using R and Python, and these regression algorithm. I mean the prediction algorithms like regression using these random forest regressions, based on the case you're talking about. This one. So building such prediction algorithms, I think it's not something too complex. We can really go and develop on our own. So I think we right on time. We have 8 o'clock. I hope these sessions helped you to some extent to get the glimpse of what are the different use cases, the areas in software engineering where we can use these AI techniques. Okay. Thank you all. If you have any more questions, please post it. I'll try to answer. This is my email ID. I'll try to respond offline and get in touch with you. Okay. Thank you and have a good day. Bye.